All right, so this week we will be starting and finishing the last chapter before we get to trig. We're going to look at two types of functions this week, exponential and log. We're going to do the same kind of thing we always do. We'll look at solving some problems, some word problems. We're going to do some sketching, transformations with each type. Okay. But the nice thing is a lot of what we already know, especially with transformations, is the same. So I'm going to put up a chart today with the A, B, C, D, and it's going to be exactly the same horizontal shift, vertical shift, all the stuff we've seen a bunch of times. All right, so first thing is I want to look at those two functions. One of them is a polynomial. The other one is exponential. Does anybody have a guess which one the polynomial is? Yeah?
X squared.
Yeah, x squared. And the 2 to the x is the exponential. What do you call, like in this one, the thing I just circled, what do you call that? That's the exponent. And what do you call the thing that's below it?
Variable.
Well, in that case, it's a variable, but in general, it's the, what is it?
The coefficient?
No, a coefficient is in front of a variable. So not the coefficient. So in general, what you would call that thing. Yeah?
Integer?
It could be an integer. That's an example of it, but it doesn't have to be. It could be a decimal, like 5.2 to the third power. The 3 is the exponent, and the 5.2 is the name of the thing always lower than the exponent. Begins with a B. Yeah?
The base.
The base. Yeah.
Or
The base. So in each of those, you have a base and you have an exponent, but they're different. X squared is a polynomial. 2 to the x is exponential. So what makes one of them exponential? What makes one of them a polynomial? Well, that's what I'm going to show you. When you have a variable for the base and an exponent that is a non-negative integer, that's a polynomial. So anything that has a variable for the base and a number in the exponent that's not negative, and it also can't be a decimal, that's called a polynomial. Those are the kinds of things that we studied back in like chapters 2 and 3, polynomials. What we're going to look at this week is more like the one that's on the right. That's an exponential. So what makes that an exponential? Two things have to happen for it to be exponential. The first one is you need to have a variable in the exponent. And the other thing is the base. The base can't be anything. It can be a lot of things, but it can't be anything. The base has to be a positive number, but it cannot be equal to 1. Right? And somebody in the last class asked me, why can't it be 1? What would happen if you had this? And you start plugging in different values for x. It does have a variable as the exponent, but it has a base that's equal to 1. So this is not exponential. Yep.
it's just going to keep equaling 1 no matter how many times you
Right. It would just keep equaling 1. 1 to the second power is 1. 1 to the third power, 1 to the fourth power. It never would change. It's always 1. So that is not exponential. And I've got a few more examples I'm going to give you right now that show you things that are exponential and things that are not. So let's start by looking at some things that are are polynomials. Let's see. Okay. So that top row, those are all exponentials. Okay. Two things they need to have: a variable for the exponent, and they have to have a base not equal to 1. And remember, the base is a real number, so decimals in the base, no problem. That's fine. The three below are not polynomials, or they're not exponentials. The first one is a polynomial, x to the third power. The second one is also a polynomial. You could think of it like this: 1/2 x to the fourth. It's got a base that's a variable, and it has an exponent that is a non-negative integer. The third one, well, that's kind of a mixture of different things. It's rational, because it's a fraction. So it's kind of a mixture of a fraction and radical, because there's a root in it. So whatever you call the third one, it's definitely not exponential. All right, so any questions on why the top three are exponential and the bottom three are not? Back here. What was that? All right, let's graph one. And let's take a look at what it looks like. To graph it, I need to pick a number for A. Let's just pick a number 2. Let's graph 2 to the x. And let's see what it looks like. So take in 2 raised to the x. Now there are two different kinds of exponential functions. This one is growing. Okay, so we call this one exponential growth. There's another kind that doesn't grow. I'll tell you the name of that one in a minute. But first, let's just look at the domain. How far left and how far right does it look like that graph in blue is going to go?
Negative infinity to like
Negative infinity to infinity, yeah. There's no indication that it's stopping. If we set y max higher, set y max to like 2,000, right, you'll see that it definitely is going to look like it goes further to the right than it did before. Right, now it's at 10. So it does keep going to the right forever, but it starts to curve up. Since it goes left and right forever, that makes the domain all real numbers. That never changes. Okay, no matter what you do to an exponential function, if you stretch it or move it, shift it, you can't change the domain. It's always all real numbers. And let's do the range. Okay. What does it look like well, let me ask you a question first. Does it look like this graph goes up forever? Yeah, it's just cut off on the edge of the screen because I don't have my x value going high enough. But remember, this is a y max of 2,000. So you can see it's definitely, it's going up forever. Does it look like it goes down forever? No. Let's zoom back in. What does it look like the lowest that graph ever goes?
0.
Yes, the lowest that it goes is 0. And if I make that a little bigger so you can see it, what we actually have is this. Anybody remember what we call that dotted line that it's getting close to?
Horizontal asymptote.
That's a horizontal asymptote. So it gets closer and closer to 0, but it never reaches it. What symbol do we use in an interval when it doesn't reach something?
Parentheses.
Parenthesis. Yep. So the range is 0, and it goes up forever. And you can tell it never reaches 0, because if you plug in a number like -5, you get 0.03. If you do -7, you get 0.007. It's just getting very close. 0.001, and then eventually now we're going to get into scientific notation. So that's 0.00003. Okay, so it's getting very, very close, but it never reaches it. Eventually, if I put in a high enough number over here, will it say 0 on the right? Yeah, because it's going to run out of decimal places. All right, so this exponent can only go up to 99. So that's 0.0 60 times, and then a 6. So it's very small. But if I do like -9,000, it's run out of decimals. It doesn't actually reach 0. Now, I told you the domain never changes. But what if I do this? What does it look like the range is now?
1, 2.
It's 1 to infinity, because what I did is I shifted it up 1 unit. So this can change. Right? Depends on if you've shifted up or down. And then I have another reminder below about A. What did I say A has to be exponential? I mentioned 2 things about it.
Positive number,
Has to be positive, but
not 1.
not 1. So that's just another reminder about that. So A is a positive real number, but it's not 1. Okay, you've already should have written that down. Talked about some exponential and not exponential. Let's look at graphing 2 to the x, and now let's add 3 to the x to it. So let's let 2 to the x draw, and then watch 3 to the x. And I want to know the difference. 2 to the x is in blue, and 3 to the x is in red. What does it look like the difference is?
It's steeper.
Yeah, 3 to the x is steeper. It curves up sharper. The bigger you make the base, the sharper that it'll start to curve up after the x-axis. So 5 to the x, I don't know how well you can see it, but it curves up even a little sharper than 3 to the x. Okay, but they all have the same basic look. All right, that's what an exponential growth looks like. Curves up to the right. Now, what they're going to ask us to do is compare and analyze other functions, but the exponent might not always be a positive number. When the exponent is not a positive number, like in that one, we need to fix it so it is, because this negative is going to mess us up. So we do not want that negative there. So how do we get rid of that? Well, there's another situation where sometimes a negative comes up, especially a -1, and I'm hoping we remember how to get rid of that from algebra. What does a to the -1 mean? Yep.
And flip it so that would be 1 over a.
Yes. When you have a negative exponent, it causes whatever was the base to flip. So what would 3 to the -2 be?
2 over -2 over 3.
No, not.
3 over -2.
Yep.
1/3 squared.
1 over 3 squared, okay, which is 1/9. Okay, how about 4 to the negative 2? What would that be?
2 over 4 squared.
What is it?
2 over 4 squared.
Not
One.
2 over 4 squared.
1 over 4 squared.
1 over 4 squared. So the negative causes the base to flip. So instead of a 3, you end up with a 1 over 3. And then when you square it, you get 1 over 9. Instead of 4, you end up with 1 over 4. And then when you square it, you would get 1/16. Right? How about one more? 2 to the negative 4th power. What would that one be?
1 over 2 to the 4th.
1 over 2 to the 4th. So instead of 2, it becomes 1 over 2. And the exponent ends up in the bottom. Okay? So that would be 1/16. So we can use that to help us fix something like this. If you have something that has a negative and it's in the exponent, to get rid of it, take your base and flip it. So instead of like a 3, make it a 1 over 3. Instead of a 4, make it a 1 over 4. And once you flip your base, then your exponent becomes positive. So 2, I'll just do one more. Let's say we add 2/3 to the negative x. If I want to get rid of that negative, take my base, flip it, so make it 3/2, and then change the letter to a positive. So that's what a negative exponent has to do with it. It's flip it. And if you ever forget, you could just put this in y1, put that in y2, and see if they look the same. They will. They'll be identical. All right, now let's look at this one. I want to compare these two graphs. But what is 2 to the negative x the same as? If you rewrite that without the negative.
1 over 2 to the x.
1 over 2 to the x. And the reason that's important is because when you are comparing exponential functions, one thing I'm going to ask you about them is this growth or is it decay? A growth graph is going to look like that. A decay graph is going to look more like that. Instead of going up to the right, it kind of flattens out to the right. And there's an easy way to tell if you have growth or decay by looking at that number. So if I asked you what the base was for f of x, what would you say? 2, and you'd be right. If I asked you what the base was for g of x, and you said 2, no, it's not 2 because of that negative. The base is 1/2. So we always want to get rid of that negative. All right, let's graph each of those and see what they look like. Well, we already have 2 to the x. If you want to type it in as 0.5, you can. Or you can type it in as 1/2 to the x, same thing. And this is going to tie in with transformations. Look at the blue one, and now look at the red one. How are they related to each other in terms of a transformation?
It's a
Yeah, reflections. And anytime that you put a negative up in the exponent, it causes a reflection, specifically horizontal. We're going to go through that in a little bit, but that's what the negative is doing. Okay, so now let's take that, let's put that over here. And let's look at that graph. Excuse me. All right, so it's asking us to find the domain and the range of each one of those. F of x is the blue one. And g of x, that's the right one. Okay, let's start with the domain. What's the domain of the blue one? How far left and right? Yeah.
Negative infinity to infinity.
Yeah, it goes left and right forever. We already talked about that. And what about the domain of the red one?
Same thing.
It's the same thing. It is also going to go left and right forever. When you have an exponential function, the domain never changes. Never. It's always negative infinity to infinity. Now, the range can change. Think of it that way. Range, change. They run. Okay, the range can change. But in this one specifically, what does it look like the lowest value we go on the blue one is? And what's the highest value?
0 infinity.
0 is the lowest, infinity is the highest. Now look at the red one. What's the lowest that the red one goes? And what's the highest?
0 infinity.
It's also 0 to infinity. Yep. What could change is the 0. If you shifted it up or down, you could make it like a 1 or something like that. Okay, any question on that? So that's a chart that describes an exponential growth and an exponential decay graph. And that was specifically if the base was a 2. Oops. If the base is a 3, a 4, a 5, it doesn't really change this chart. And that's what I kind of want to generalize over on the right. So now, instead of a being specifically a 2, pretend like a is any positive real number. Except what? 1. I should have written that down. So a is any positive real number except 1. All that the base is going to do is change the steepness of the curve, but it's still going to have the same general look. Okay, so bless you. So the blue one represents exponential growth, and it's going to look something like that, maybe a little steeper, maybe less steep. And the red one is representing what we call exponential decay. So let's start with the blue one, f of x. On the blue graph, as x approaches infinity, means you're heading which way? Yeah? Well, as x approaches infinity. Think of which way the x-axis goes. To the right, yeah. So as you go to the right, what's happening to the y value? So if you trace along the blue graph as you head to the right, what happens to the y value? It approaches infinity. Yep. Now on the blue graph, as x approaches negative infinity, what happens to the y value there?
Approaches 0.
It approaches 0. That's generally how all exponential functions will behave. As you head to the right, you approach infinity. As you head to the left, I'm not going to say you always approach 0, but I'll say you approach a number. It'll flatten out to something. All right, now let's look at the red one. In the red graph, as x approaches infinity, what does y approach there? Yep, it'll approach some number, in this case 0. How about as x approaches negative infinity? It will approach infinity. Yep. So that's the behavior of a decay graph. So whether you are growth or decay all depends on that number that I just circled. What do you think that number would have to be above to be growth? Or what do you think it would have to be below to be decay?
0 to be growth.
Well, it always has to be above 0 because that's the definition of an exponential. It always has to be a positive base, so it'll never be below 0.
Above 1.
Above 1 would be
Oh,
growth.
Yeah.
And what about decay?
Between 0 and 1.
Between 0 and 1. Yep, exactly.
Just bathroom real quick.
Yeah. Okay, so the key difference between those was the base, greater than 1. You have growth. Between 0 and 1, you have decay. So we're going to look at, towards the end, we're going to look at a couple applications. Some of them will be growth, some will be decay. The next thing I think we're going to look at is the transformations. Okay, so transformations, they work exactly the same for every function we've done all year. All right, so I'll put up a chart. In this chart, it doesn't matter what the base is. Okay, I'm going to do an example in a minute where the base is 3. But the base, that doesn't affect the transformations. It's everything else around it. X, A, D, times C. Okay, so we just want to make sure we know what the A, the B, and the C and D do. When you are asked to list or describe transformations, you've got to make sure you put them in the right order. And that's what this next question is going to ask. And that's why I've labeled them A, B, C, D. That's the order. So the A and the B are inside the exponent. Does anybody remember which direction the inside stuff affects? Horizontal, yes. The A and the B affect horizontal. The C and the D are outside the exponent. So the C and the D are going to affect vertical. Okay, now I'm going to break it down a little bit more. Specifically, the A is addition or subtraction. Does anybody remember what type of horizontal transformation addition or subtraction is? That is a shift. Yep. So A is your horizontal shift. And positive would move it which way? Yes, it is backwards. Everything horizontal is backwards. Positive is left. Okay, so now the next one is B. B is still horizontal because it's inside the exponent, but it's multiplication, so it's not a shift. It's a stretch. It is a stretch. So let me just do an example of that. If you had 2 to the 3x. Again, it's horizontal. You might think, oh, 3 makes it 3 times as big. Nope, makes it 3 times as small. So that's a horizontal stretch by 1/3. If you had something like 2 to the 1/4 x, that one you might think, oh, 1/4, small number makes it smaller. Nope, small number stretches it bigger. So that's a horizontal stretch by a factor of 4. Okay, so horizontal is backwards. Okay, so here's your horizontal. goes with B. There's your horizontal shift. That goes with A. All right, let's do C. Now we are outside the exponent. So it's vertical, and it's multiplication. So anybody think they know what C is going to do? Vertical stretch. Yep. And the vertical is not backwards. Okay? So if you had something like 4 times 2 to the x, vertical stretch by factor of 4. 4 does make it bigger. 1/3 times 2 to the x makes it smaller. It's one vertical stretch by 1/3. Okay, so that's C. And D. This is actually one I showed you an example of when I changed the range. What does D do? Yep, that's your vertical shift. Positive would move it up, and negative would move it down. Okay, now there are always 6 transformations. That describes 4. The B and the C can each do something else. And we've already seen an example specifically with the B in this picture right here. What happens if B is negative? Yeah, we get a reflection. If the B is a negative, it causes a horizontal reflection. So I'm just going to add that as like a note at the bottom. If B is negative, we have a horizontal reflection over the y-axis. And one more note, if C is negative, we have a vertical reflection. And vertical is over the x-axis. So that gives us a total of 6 transformations. A is your horizontal shift, B is your horizontal stretch and horizontal reflection, C is your vertical stretch and vertical reflection, and D is your vertical shift. Okay, so I'll keep that chart up while we try the next example. Okay, so it says in example 2, list the transformations to turn f of x into g of x. Okay, so first first thing is always good to get an idea of how many transformations there are. How many? Yep, there are 3. So go in order. Start with A, then go to B, then C, then D. Okay, let's start with A. Is there a number in the spot for A in this problem?
Yeah.
Yep, what is the number? It's a positive 1. What does a positive 1 in the A spot do?
Horizontal shift to the right.
Horizontal shift
Yeah, to the left.
left. Yeah, left 1. So shift left 1. Perfect. Okay, let's go to B. Is there a number in the spot for B? No, well, I mean, there is a number, it's just, it's like having a 1x. So nothing's happening with B. Okay, is there a spot in C? A number in the spot for C? Yep, what's that number? 2. So what is a 2 going to do?
Vertical stretch.
Yep.
2 backwards 2.
So vertical stretch factor of 2. Okay, so we got C. Last spot, D. Is there a number in the spot for D? Yep. What's the number there? It's a -5, and that's going to do what? Yep, shift down 5. Each transformation really has 2 things you need to describe, a direction and a how much. Left, 5, right, 2, up, 3. So you have direction and then a how much. Vertical stretch by 2, things like that. Okay, any question on those 3 transformations? And at most you can have how many? If it had every single one in the same problem? 6. Up to 6. Okay, that we're gonna talk more about the number E tomorrow. E is, it's a constant like pi. You're probably more familiar with pi is 3.14. Well, in math, E is 2.718. And it has a special meaning, like 3.14. And we'll talk about it tomorrow. So not today. All right, so the last thing is looking at a couple applications of exponential growth and exponential decay. First of all, for something to be exponentially growing or decaying, it has to be increasing or decreasing by a percentage. That's what makes something exponential. It is increasing or decreasing by a percentage. If I said to you, the town is growing at a rate of 100 people every year, that's not exponential. That's growth, but it's linear. Straight line growth, right? You're just adding 100 people every year to the population. If I said to you the population of the town is going up by 10% every year, that's exponential. Okay? Over time, it's going to go up very fast, much faster than linear. This is the formula that you need when you're doing a problem with exponential growth. Okay, so a couple things about the formula. It has 3 letters in it. P stands for some kind of an initial amount. Could be an initial amount of people, could be an initial amount of bacteria. If we were going to be doing the banking and finance sections, it would be an initial amount of money. But it's a starting amount. The next thing next to that in parentheses is 1 plus R. R is the rate. And for exponential growth, you're probably going to see a word in the problem that says increase, like the population is increasing. The number of bacteria is increasing, going up, okay, something like that. The other important thing about R is it has to be a decimal. So if I told you that the population was going up by 12%, how would you rewrite 12% as a decimal? Yep. 0.12. 4%, 0.04. Okay. 0.12. So if you see a percentage, make sure you change it to a decimal. And then T, that's just how much time has gone by. We want to know the population in 5 years, 10 years, how much time. Now, to change that to exponential decay, there's only one thing that has to change in that whole formula. Yeah, this is going to turn into a what?
Negative.
It turns into a negative. So instead of a rate of increase, it's a rate of decrease. I'm not going to relabel what all of them stand for because it's the same as up above. It is up to you when you read the problem to determine if it's exponential growth or decay. So let's look at our first problem. What in that sentence tells you that this is a problem that's going to involve an exponential formula?
Increasing.
If I said the population of the town is increasing by 100 people every year, it does have the word increasing, but that would not be exponential.
0.5%.
Right. The fact that you see a rate of change that is a percentage, that tells you that it is exponential. The increasing tells you the type, now that we know it's exponential. So is this growth or decay? This is growth because of the word increasing. So increasing is still important. It tells you something different. Okay, so the first thing they want us to do is model this with a function. Let's do that first. Now, you can use any letter for the name of your function. I would use P because we're talking about people or population. So we're going to write population as a function of time. Okay. In an exponential growth problem, what's the first thing that comes after the equal sign? Well, in general, what does that stand for?
The initial amount.
The initial amount, whatever that is. What's the initial amount in this problem? 50,000. Okay, and again, nothing specific yet, but what do you always put in the parentheses for exponential growth? 1 plus r. Yep, 1 plus r. So in this one, it's going to be 1 plus, what am I going to put after the plus sign? 0.025, yep. And I need one more thing, and without this, it is definitely not exponential. Time, and where does that go? That's my exponent, yep. So when I combine these together, that's going to be my final answer. 50,000 times, what's 1 plus 0.025? 1.025 to the t. So that's the first part. Model it with a function. And now the second part is graph that and figure out when the population hits 100,000. Okay, well, let's graph it. Okay, so we got 50,000 times 1.025. Make sure you do use x, because that's the variable the calculator needs to use. And now let's think a little bit about the population. Right now, the population is going from -10 to 10. Is that going to be a good window? No. What's the smallest that the population can be in this problem? Well, in this particular problem, the population can't reach 0. 50,000. I agree that if you asked about a population in general, it can't go below 0, but this one we know can't go below 50,000. And we're going to be checking to see where it hits what?
100,000.
100, so I'd go a little extra. We have 125,000. Okay, X, that's taking the place of the T. T is time. What's the smallest amount of time that could go by in this problem? How much?
0.
0, yeah. We could decide to just check the population at the beginning of the experiment before any time goes by, and that's 50,000. The most amount of time that could go by, well, we don't have a limit on that. We can go as many years as we want. Our goal is to see when we hit 100,000. If we don't hit 100 within 35 years, I'm just going to make my graph go a little further. But let's try 35 years. So there's our population. Okay, it is exponential. It doesn't look, hopefully it doesn't look linear to you. It is curved. But it's a slow curve because it's not a big percent. It's only 2.5%. All right, and what else do you think I need to add to my y equals screen to answer the second part of this question? Yep.
Y2 equals 100,000.
Yeah, I need to put in 100,000. Okay, so now I can see my population growing. I got to mark it 100,000. What do I have to find now?
The intersection.
The intersection. All right. So rounded to 2 decimal places. How many years is it going to take, essentially, for the population to double? That's what this question is asking.
20.07.
Yeah. So it's going to take population will be 100,000 in 28.07 years. Now, there's a reason why I said specifically to use the graph and not algebra. What about this equation would make it harder to solve with algebra? It's definitely not an equation you would see in Algebra 1. Yeah?
The exponent.
What about it?
It's a variable.
Right, the variable is in the exponent. The only way that you can solve a problem that has a variable in the exponent is with a logarithm. That's how you have to do it. So we would need to learn those, and that's what we're going to learn later on this week. All right. If you were going to solve it algebraically, you would fill in 100,000 right there. And you could at least divide by 50,000 to get that on the other side, but at that point you'd be stuck. You wouldn't, or I haven't taught you how to get rid of that t yet. So that's why we did it graphically. All right, any questions on that one? So that's an exponential growth problem where they specifically give you a percentage. Oh yeah, always be careful about including negatives because sometimes negatives don't make sense, like negative people, negative time, things like that. Well, I guess you can have negative people, but not a negative number of people. Okay, so the next type of exponential growth is specifically something doubling. In this kind of problem, I would not tell you what the percentage growth is. You have to know it because it will specifically say doubling. So let's see if we can figure out what that means. So let's start with 100 bacteria and double it every hour. What would be the amount of bacteria at the very beginning of the experiment before any time has gone by, based on what they gave us?
100.
Right, we're starting with 100. After 1 hour has gone by, how much bacteria would you have?
200.
You would have 200. But in order to see the pattern, I want you to think of it as the initial amount times 2 to the number of hours that have gone by, 2 to the first. Right? How many bacteria would we have after 2 hours? 400. Or it's the initial amount times 2 to the number of hours that have gone by. So after 3 hours, we would have 800. But can anybody think of it more in the pattern on the right? And that's going to help us with the next question, which is t hours. Yep.
100 times 2 to the power of 3.
100 times 2 to the power of 3. And now what would be the formula after t hours based on the pattern?
100 times 2 to the power of t.
100 times 2 to the power of t. What is that 100? Right. So that's the formula. It's initial amount times 2 to the t. So you have to know that when you are doing a doubling problem, what goes after the initial amount is always a 2. And that's because doubling is 100% growth. A lot of people think doubling means 200% growth. Nope. Doubling is 100% growth. It's like if you were making $15 an hour and you get a 100% raise, you would be making $30 an hour. That's doubling. The other thing you notice here is that exponent. It's t divided by the length of time to double. That's because the exponent has to be the number of doubling cycles. It cannot be the amount of time that has gone by. If they're the same, then that's a coincidence. But it has to be the number of doubling cycles. If something is doubling every 1 hour, then yes, the number of hours that have gone by will be the number of times it is doubled. 2 hours, doubled twice. 3 hours, 3 times. But let's say something doubled every 5 hours. If 10 hours have gone by and it doubles every 5, how many times would it have doubled? Yep. Twice, right. If 10 hours have gone by and something doubles every 5, it would have doubled twice. So if you're doing a problem with that information, the exponent here would need to represent the number of doubling cycles, not how many hours have gone by. And that's how you find the number of doubling cycles. Take the time and divide by the length of time to double. Okay, so let's set an example up. We don't have to graph it because the graph is the same as the population of the town. You end up with something like this. And you just find an intercept. Okay, but I just want to make sure people know how to set up that equation. So we've got 100 bacteria starting out in a petri dish, and the bacteria is going to double every 3 hours. I want to know when there'll be 350,000. And you might think, well, it's going to take a while. It doesn't really take that long, right? If you want to just kind of ballpark it, you can just take 100, keep doubling it, so that's 1. That's 2, 3, 4, 5, 6, 7, 8, 9, that's 10. That's 11. And at 12, I've gone past it. So it's somewhere between 11 and 12 doubling cycles that have to happen. And how often does it double? It doubles every 3 hours, and it's going to happen between 11 and 12 cycles. So that's between the 33 and the 36 hour mark. That's when it'll hit that many. So somewhere between 33 and 36 hours. So just about a day and a half. But let's set up the equation and see if we could have something we would plug in. What's the first thing that's going to come after the equal sign?
100.
Finish up.
Yep, initial amount, which in this case is how much? 100, yep. Now, normally you do 1 plus r, but it's doubling, so you put something special there. What do we put there for doubling?
2.
2. It's always a 2. I wouldn't tell you it's a 2. You need to know that. It's 2. And what about my exponent?
3.
T divided by 3. Remember, it's the time divided by the doubling period. How many hours does it take? Okay, so there's your formula. And now there's two kinds of questions I could ask you based on that formula. I could say, tell me how many bacteria you would have after 20 hours. Or tell me how many hours it would take to get to 350,000 bacteria. I'm asking the second one. Where does this 350,000 get plugged in?
Why 2?
T, well, would it be the T or the A of T? Right, because it's a Y value. That is not a T value. Okay, that's not a time. It's an amount. So that would go right there. Okay, and we got time. We can quickly find the answer. We said it's between 33 and 36 hours. Well, let's see. Put that in Y2. Put your equation in Y1, but clear the old one first. 100 times 2. I don't know if you need parentheses around the exponent. I don't think you do. Okay, now we're looking for where we hit how much bacteria?
300.
So let's go 350. And we're starting with how much?
100.
Whether you put it at 100 or 0, you're not going to be able to tell the difference on the screen because it's going to be so zoomed out anyway, you wouldn't tell the difference. And we already know it's between 33 and 36 hours. We already estimated that. So that gives us kind of an idea. Let's set that at 40. Okay, it doesn't look like much is happening with the bacteria, but then all of a sudden, it just takes off and goes almost vertical. I thought I set it higher than that. I meant to do 400,000, which I thought would have been a little higher. Oh, I set my Y max right at 350. Well, it's okay. It's just on the edge of the screen. Should still work. Exactly in the interval we said. It's going to take 35.32 hours. So you can get an estimate, like we did, by just doubling it by hand and watch it. But to get a more exact answer, you either need to graph it or use a logarithm. Good. Any questions on that? Okay, so last problem is going to be the opposite of doubling. Anybody know what that is? Halving, yeah. Instead of doubling each time, take half. And halving is a specific type of exponential decay. Specifically, halving is a 50% decay problem. That's the percentage, 50%. That's what you're left with each time. So a lot of times where you might see something about half-life is if you talk about radioactive material. So let's say like at a nuclear power plant, there's byproducts of nuclear energy, and one of them is radioactive waste. And let's say that waste has a half-life of 1,000 years. So if you produce 100 pounds of waste today, 1,000 years from now, that 100 pounds will be down to 50. In another 1,000 years, that 50 will be down to 25. In another 1,000 years from that, it'll be down to 12.5. It keeps getting cut in half every 1,000 years. Now, if you keep cutting something in half, what number does it get close to, but it never reaches? Right, never reaches zero. So technically, once you create that waste, it's never really gone. It gets small enough that it becomes less harmful, or it's safe, but it's never really gone. A lot of medications kind of have the same idea to them. Like when you take a medication, it might have a half-life to it. So if you take like 10 milligrams of something, and it has a half-life of 12 hours, that means halfway through the day, 12 hours later, that 10 milligrams you took is now down to 5. And then another 12 hours later, it's down to 2.5. But if you keep taking another pill every 24 hours, what happens is over time, the amount of medication starts to stabilize. Because it's like you have several pills in you at the same time, and each one of them is at a different rate of decay. So it starts to even out. And that's what we call like the steady state level of medication that's in your system. If you start skipping a dose or something, then you start messing with that. Then it gets messed up. So yeah, all kinds of things have half-lives. And the formula for a half-life, it's very similar to doubling, except instead of a 2, you use a 1/2. It's initial amount times 1/2, and the exponent has to be the number of half-life cycles. So in our problem, we're going to do something that has a half-life cycle of 20 days. I would think if that, I mean, this is about radioactive, but if that was a medication, I would think that's a very long half-life. If you think about it, you take a medication and it takes 20 days for half of that medication to leave your system, that's a pretty long time. I don't think most medications stay in someone's system that long. Okay, but this is about radioactive stuff anyway. So. All right, so let's write an equation. Since we are solving for an amount, I would name the function a. And it's going to be an amount as a function of time. What would come right after the equal sign? Yep, and in this case, what is the initial amount? 5. After that is normally in a decay problem, 1 minus r. But I didn't give you a percentage because I used that word. What's going to go in the parentheses? Yep, that's going to be a 1/2. And what's the exponent going to be? T divided by 20. Okay, so let's just kind of get a ballpark of when that's going to happen. How many halving cycles does it take to turn 5 grams into, let's see what they want us to find, 1 gram. Okay, so we already did part 1. Let's turn 5 grams into 1 gram. So let's take 5, divide it by 2. That's 1 half-life cycle. There's 2. There's 3. So it's somewhere between the second and the third cycle that we're going to go under a gram. How many days would that be if it's between 2 and 3 cycles? Somewhere between 40 to 60 days, because each cycle is 20 days long. Where between 40 and 60? That's what we need to figure out. Okay. Where would that 1 gram get plugged in? Is that time or is that an amount? That's an amount. So we're going to fill that in right there. And we're going to solve this problem like we were trying to find the time to hit exactly 1 gram. That is not the question, though. The question is less than 1 gram. But that's okay. Solving when we're exactly 1 gram will still give us the answer. You just have to write it the right way. Okay, so what's going to go on y1?
5 times 1/2 to t over 20.
Yep, 5 times 1/2. If you want to use 0.5, that's fine. If that was 1/3, though, you would want to use 1/3. Don't use 0.3. 0.3 is not 1/3. So you got to use the exact number. And then what's going to go on y2?
1g.
1. Okay, in my window, x is the amount of days that need to go by. We already know it's between 2 and 3 halving cycles. So it's not going to be more than 60 days. Well, my substance is decaying. So what's the amount of my substance that I start with? 5, and we will never have above that. It's going to decay. What's the lowest that it can decay to but never reach? Right, it can never really reach 0. All right, so let's use that as your window. Hit graph. Okay, there's your substance decaying exponentially. And we know we're going to hit it because we already checked that. What do I have to find now?
The intersection.
Find the intersect. Good. Now, we've got to be careful with how we write the answer. That is the amount of time. At 46.44 days, you will have exactly 1 gram left. We want to have less than 1 gram. So how would I write my answer? I want to round it to 46.44, but I've got to say more than 46.44.
T is greater than 46.4.
Yes. So the number of days is greater than, has to be more than 46.44. Sometimes people see the word less than here, and they say the number of days has to be less than 46.44. But if you're less than 46 days, you're going to be up in this section. That's not the section they want. They want to be under the red line, which is past 46 days. Any questions on that? All right, so that is exponentials. I do need to just adjust 2 questions. 27 is okay. Okay, 31 involves the letter E. I just haven't shown you how to press that on the calculator yet, so we're going to talk about that tomorrow. And so does 35. Okay, so that's the homework. And remember, you guys are at the same point, just coincidence as my other class. So make sure you check the video from pre-cal, not algebra 3.